right, let's take a look at our lesson that focuses on the natural base E. So just some information. So it's called the Euler number. I know it looks like Euler, but I think it's a German mathematician, so it's the Euler number. And this is the definition that we use in calculus. Of course, you're not going to have to memorize these definitions. I just wanted to get you'd have a feel on what's going on. So that's a definition of E, the Euler number, in calculus. We have another definition. Do you remember these little exclamation point things? Remember that? Factorial notation. This is just an alternative definition. If you recall, 0 factorial is 1. I know that's weird, isn't it? But it is. 0 factorial is 1, and so is 1 factorial. So E, or the Euler number, actually is a number. For years you've known about pi, right? Pi is about like 3.14, 15, blah, blah, blah. Well, the Euler number is also a number. It's about 2.7, and more. It's just a number. So that's just something that we're going to be introduced to today, how we use that. Let's look at some exponential functions. So here's our Euler number, E. And what this is saying is basically it's identifying, we can look at the equation and identify whether this is an exponential growth or exponential decay function. These are going to become important to us as we move along in this unit. We're going to be working on applications or word problems that involve exponential growth and decay. Okay, so it's growth, exponential growth, if that variable, this one right here, A, is positive, and R, which is right here, is positive. Okay, that's pretty straightforward. So let's look at decay. It's exponential decay. Notice that A is also positive, but this time R would be negative. So the number in front of the x, and the exponent would be negative. So that's how we can tell by just looking at an equation whether it's exponential growth or decay. All right, so let's look at graphing. So for purposes of graphing, graphing is not the most precise thing that we do. So for purposes of graphing, we're going to think that E is just about 3. It's about 3. We can use 2.7 if we're just using a 2.7, but if we're going to square it or do something crazy to it, let's just think about it as a 3. So I'm not going to mess with the fractional ones. Let's work on we're basically going to find these points and plot them. So we would do like e to the negative 2. That would be the same as 1 over e squared. E, which would actually be 1 over, say, 2.7 squared. I don't know about you, but I don't want to square 2.7. I would rather, square 3. So we're going to go with the 1/9. Okay. So e to the negative 1 would be 1 over e, which would be like 1 over 2.7. Again, I don't want to try to figure out what 1 over 2.7 is, so I'm going to go with 1/3 because we're just graphing. It's not going to be that much different than 1/3. E to the 0, we know anything to the 0 is 1, and e to the 1, well, that's easy. I can do 2.7 to the first, so it's just 2.7. All right, so let's remind ourselves from the previous unit, we did a little bit of graphing, or actually this previous lesson, I think it was the first lesson in this unit, and we hopefully remember that all exponentials have at least one horizontal asymptote. So the parent exponentials, have horizontal asymptote. I'm just going to abbreviate it as HA, horizontal asymptote. is always y equals 0. Okay, so that's for the parents. Well, what do I mean by a parent? Now the parent would be, there's no like transformations. There's no like +2 here, or there's no like 2 there. I mean, there's nothing going on. It's just e to the x. All right, so we do have a horizontal asymptote at y equals 0. So let's go ahead and draw it in. Okay, this is our horizontal asymptote. All right, so now let's plot our points. So we've got -2 and then 1/9, and maybe about right there, -1, 1/3, 0, 1, then we have 1 and about 2.7, so maybe somewhere like that. All right, and there is our graph of e to the x. Okay, so looking at the graph, you know, it's as we read it from left to right, it's getting bigger and bigger. So looking at the graph, hopefully we can tell that this is a growth. This is exponential growth. If we looked at the equation, we could also tell that it's exponential growth because this number is positive. Okay, the number in front of the x is positive, so yes, that's the exponential growth. We could tell two ways because we graphed it. All right, so now let's graph this one, e to the negative x. Okay, again, I don't want to mess with the decimals. We'll get a pretty good picture with just these numbers anyway. So I've got e to the -1, which would be e to the first. Right, negative is a positive, and so that's just 2.7. Then we have e to the 0 would be 1. E to the -1, we did that up here, right? E to the -1 we decided was going to be 1/3, and e to the -2 we decided was going to be 1/9. All right, so now it's a parent. This is a parent one, so function, so the horizontal asymptote is going to be right there. All right, so let's plot these points. So see -1, 2.7, 0, 1, 1 and 1 would be at 1/3, and then 2 would be at 1/9. Okay. All right, so as we look at this one, reading it from left to right, we see that it's falling, it's decreasing. So just by the graph itself, it looks like a decay, but, and it is, so this is a decay, this one is decay. We could also tell by simply looking at the function, and we see that this is a negative, and so that's also a way we can tell that this would be exponential decay. All right, so let's look at these examples where we're just going to look at the function and decide whether this is growth or decay, exponential growth or decay. The first one, I hope that you can, you know, work with me here. Remember, we're just looking at this sign. We see that it's negative, so that means that this one is decay. This one, 4 is positive, so this one is growth. All right. Okay, so now let's take a look at some more examples on the next slide. Okay, so we want to simplify. The first thing that we would do is we're going to look at 18/3. We're going to work with that. So we know how to simplify 18/3, right? 18 divided by 3 is 6. E to the 6 over e squared. Let's think about our exponent rules. Remember, when we're dividing, these bases are common, right? E, this is the same base. When we're dividing terms with the same base in it, then we would subtract the exponent. So 6 minus 2, it would give me a 4. And so that's just an example of simplifying with ease in the expression. Okay, so let's look at number 6. You certainly have a choice. You could take the 3 and distribute it to all of these 4 individual things in here that are connected by multiplication. Well, you know me, I don't really like big numbers. So I'm going to deal with this inside part first. I'm going to go ahead and multiply the 4 times 3 and get the 12. And the e to the 8 times e to the negative 5th. Okay, we're multiplying common basis. Do you remember what you do the exponents? Yes, you add. So 8 plus a negative 5 would be 3. Okay, so that's much better for me. I have less to deal with and they're smaller. So now we know that this 3 right here would be distributed to each item because they're connected by multiplication. I really hope that we've gotten that desire out of us to distribute over and adding or subtracting. I hope that's true. Fingers crossed. Because this is not okay. That is not okay. You cannot do that with the plus or minus. Okay. All right, so then I've got 12 cubed. Let's see, we've got power to power here, 3. The exponent is 3 raised to the 3. Do we remember the rule for power to power? Yes, that's multiplying. So 3 times 3 would give me 9. Now I'm not going to ask you to multiply out 12 times 12 times 12. We can just stop here. I mean, if you had a calculator, you could see it's 1728. But we will just leave it as 12 cubed. Okay. So now let's practice. Let's go into logarithms. So ln, this little thing right here, ln is it's called the natural log. That's its name. It's a log and it uses all of the regular log properties that you've learned also apply to natural log. Natural log is simply a log with the base of e. So when we see this ln written here, right here, there's an invisible e there. That's an implied e. Some students really like to write it, so you can write that if you want to. You don't have to. Like if you recall, we talked about log. If log, let's say log of x, if log doesn't have a base written, do you remember what the implied base is? Yep, that's right, it's a 10. Okay, so ln has an implied base of e. Okay, so we're going to, like I said, we're going to use all those rules that we used with regular LOGs. Okay, so here, this next one, we're going to go back and forth. We're going to go from log notation to exponential notation and then back. Okay, so remember there's an e right here. Do you remember the circly thing that we looked at last time? Remember, it's like a little circle, so we circled that and then we went around and we did that. Remember when we did that to transform a log into an exponential? So it'd be e to the 1.609 equals 5. And I'm just rewriting it. That's all it asked me to do, is just to rewrite it. Now going from an exponential to a log is more challenging for some students. What I want you to really kind of think about is that this base is the same as this base. The base of the exponential is the base of the log. So if I have a base, my exponential base is e, then the logarithm is going to be ln. I'll just write it and print it. So it's ln. So that takes care of the e. Okay, so then we, and actually you could do the whole circly thing with this too if you wanted to. You would turn that into a log and then you would make this the argument and that the answer. So ln of 0.086 is 3. Okay, so you can think about that with a circly thing also. All right, so let's take a look at these here on the bottom. They want us to evaluate. Okay, it looks weird. So let's go back. I want to remind you of something that we've done previously. If we go back to here. Remember this right here? Remember when it told us to evaluate and we said that x represents the answer and we set it equal to x and then we converted? We're going to do the same thing. We're going to virtually do the exact same thing on this lesson. We're going to set it equal to x because it says, it says evaluate. This is one way to work these problems. So x is the answer. We're introducing x. There's not really a x, variable x here, so we're going to make it equal to x. So let's do our circle thing. So e to the x equals e to the 4. So we know from our rules in the last unit that when our bases are the same and they're equal to each other, that we can set the exponents equal to each other. So this answer is a 4. And I want you to start looking. See this ln e? It just collapsed and it gave you a 4. Why? Why would it do that? Well, ln e to the 4th, I can use log rules. Remember the log rule that works with exponents? You just bring it down to the front. So 4 ln e, and it's a value. So ln e is actually 1, and 4 times 1 is 4. So that's why it works, because ln e is 1. Okay. All right, so using that thought process here, if this part collapses, then my answer should just be x. Okay, let's test that with this whole process where we, set it equal to x. Okay, let's set it equal to a, so the x's and x isn't the same. So e to the a equals e to the x. So a is x, so our answer is a. So this does collapse to x. All right, I can't tell you how important that is. I had in calculus this week, we looked at that. It just doesn't go away. The last ones, these are really small little equations that we're going to work on the notes. In the practice, you have some larger ones. I just want us to get the idea. So we have solved log equations before. If you recall, if there's a log like equal to a number, then you have to convert. Remember, you have to convert into an exponential. And you can't convert until there's just a 1. There can only be like a 1 in front of here. We can't have anything else. So we would do e to the 4th equals 5x. And in solving for x, I would want to get rid of the 5 by dividing. So x is basically e to the 4th over 5. And that's all. We don't want to, we're going to just leave e in the answer. There's no sense in like doing 2.7 times, 4 times and all that kind of stuff. It would be much simpler if we just left e there. All right, last one. So here we go. This is a 1 in here, so we're good. We don't have to move anything. So let's convert. So I've got, this is an e. So e to the 1/4 equals 1/2 x. I want to get x by itself, so I would have to get rid of the 1/2 by multiplying both sides by 2. So I've got 2e to the 1/4 equals x, and that's it.